Oftentimes in chemical engineering, we mention compositions of the distillate in the bottom streams and whatever concentrations at a particular plate. And in practice, while we can stick to the theory and make all these assumptions, it pays to know how we actually verify the true concentrations present in a solution. And so in distillation, for example, or in fermentation, when we are very interested in determining the ratio of the ethanol to water that is present in a solution, we turn to gas chromatography, or GC for short. And gas chromatography is what allows us to be able to derive pretty quickly the concentrations in solutions, assuming that we already know what we're looking for. We already know that water and ethanol are in our solution. And so what you'll commonly find in labs are GCMS. So we would hook up a mass spectrometer to the end of the gas chromatographer in order to determine the identity of whatever molecules are present in your solution at a particular point in time. And so with that, I'll discuss in this video how gas chromatography works, and then we can talk about mass spectroscopy later. And so the way it works is, like any other form of chromatography, we rely on a stationary phase and a mobile phase. And in the case of gas chromatography, our mobile phase will be some kind of carrier gas. And generally it'll be like nitrogen. And the stationary phase can be a liquid or a solid. And what you'll do is, in a distillation column, for example, if we wanted to know what the distillate composition is, we would take a syringe and extract a small amount. It doesn't even need to be a milliliter. It can actually be 1 microliter of solution, and we would place it into our gas chromatographer. And so the gas chromatographer will have some pressurized tank containing your carrier gas, and the carrier gas will have a valve present to control the flow, and we will also have an injection port. And inside the chromatographer machine, there'll be many feet of coil to travel through before we reach a detector. And the detector will allow us to visually see some kind of curve that tells us over time whether or not a particular molecule was recognized. And so what we'll get is some kind of peak that will spike and then spike at a later time. And in this case, because we knew beforehand what molecules we're looking for, we would know molecule A and molecule B emerged. And within these coils in your chromatographer machine is where our stationary phase will be located. And what we do, like in NMR, to determine the relative ratios between these two or multiple components in your solution is integrate the area under these curves and then analyze the ratio of the areas. And that will tell us what the relative concentration is of these two components. And another thing that one should note from chromatography is the rate at which these two species A and B will travel through our chromatographer machine are dependent on their affinity for the stationary and or mobile phase. And so looking at this compound A, we know because A emerged through our chromatographer machine faster than did B, it means that compound A has a higher affinity for the for the mobile phase, and or a lower affinity for the stationary phase. And so if we think of chromatography like some kind of race between two molecules, if relative to B. So in the case of B, because B was so much more attracted to the stationary phase and less attracted to the mobile phase, it's taking it a longer time to flow through our system. And so that's how we're able to separate these solutions and identify the number of components we have. But if we do not know what is present in our solution, again, we will have to turn to mass spectroscopy in order to determine that. So this concludes how we use gas chromatography in practice to determine compositions of already known fluids. And I hope you guys find this useful. Let me know if you have any questions, and thanks for watching.